So welcome everybody to our next webinar. Today's topic will be timeouts in RxJava, as well as comparing and contrasting timeouts in RxJava with timeouts with Completable Futures. This example is something we've actually gone over before in the context of Completable Futures, and now we're going to revisit it in the context of RxJava, but we'll also come back and take a look at it from the Completable Futures version now that we've had a chance to look at both examples. So without further ado, let me go ahead and share my screen. Alrighty, let's see, here we go. So you should be seeing my screen here. Let's first just take a quick synopsis of what we're going to cover today. So if you go to my live lessons repository on my GitHub account and you go down a little bit, you'll find a bunch of RxJava examples. And if you click on this, we'll go to EX5. So that's what we're going to be looking at today. So please feel free to go ahead and clone the repository and follow along with what we're about to cover. So now let's go ahead and switch over to my IDE. So you can see here that what we have is my RxJava project open up in IntelliJ. Let's take a quick look and just kind of get a lay of the land for this. So we're going to define a few fields here. One of them is going to be something I call default rate S, which is a default rate for singles. And then there's also something called default rate F, which is going to be a default rate percentage for flowables. And you'll see in a second why we have two different versions, one for singles and one for flowables, because we're going to have two different implementations demonstrating timeouts in two different ways with RxJava. Then we come down here to the number of iterations for the test, and you'll see that we're going to do this about 5 times. You can crank it up a bit, but I think it'll demonstrate what we need to do in that amount of time. Over here, we generate a random number generator, and you'll see why we need that in a second as well. So armed with that as background, now we go ahead into our main function, and we're going to start the test running. And so we're going to have 2 different tests demonstrated for RxJava. The first is going to be using Concurrent Singles, and the second test is going to be using parallel flowables. And you'll see in a minute why I chose both versions. Parallel flowables is a newer feature. It's a RxJava 2 feature, whereas, of course, things like observables and singles have been around for a long time. So let's go ahead and take a look here. Here's run concurrent singles. And as you can see, we print off that we're entering the test, and then we're going to go into a number of iterations. You'll see what that does when we run the test in a moment. So now let's go ahead and make ourselves a couple of singles. Now keep in mind, of course, in RxJava, everything is lazily performed. So the operations that we're defining here actually don't do anything until we start subscribing and actually having the data pushed through the stream at us. What we're going to do here is we're going to use a single because we're just trying to get a single value, and we're going to use the factory method from callable, which is going to go ahead and call this method. We'll look at the method in a second. And the method is known as FindBestPrice. And so what it's going to be doing is looking for the best price between London and New York City. Now, of course, this is anticipating or expecting to be used with a real web service where we've got some kind of price finder running in the background as a microservice or whatnot. I'm actually just going to mimic that here. I'm not actually going to be hooking it up to a real price finder, but you'll get a chance to see what this does in a second. Then what we're going to do is we're going to take this and we're going to compose it together with a single pool subscribe on mechanism. So we're going to take a look at that here in a second. What that's going to do is that's going to go ahead and subscribe this operation to run in the common fork join pool. And we'll look at that momentarily as well. So that's what we're going to do here. We're going to go ahead and have a computation that runs in a thread in the background in the common fork join pool to find the best price. And we'll look at the details momentarily. The next thing we're going to do is we're going to have another single, and this is going to go ahead and query for an exchange rate. And the exchange rate is going to be basically US dollars to British pounds. And so in this particular case, we use the from callable factory method again. This is also, as we'll see in a second, going to be running in the background in a thread from the common fork join pool. Except this time we're going to stick a timeout on this. And what we're doing here is we're saying, if this query to see if we can get the current exchange rate takes more than 2 seconds to run, then we're going to use the default exchange rate. And remember, the default exchange rate up here was just set to be 1.0. Probably completely unrealistic, of course, but you could change that to any value you wanted to between pounds and dollars. I don't know what the current exchange rate is, but I'm sure it's not 1-to-1. And then down here, we're going to have this also running in a thread from the common fork join pool, and I'll show you how that works in a second. So we'll look at the details here in just a minute. I'm trying to give you the big picture view of what we're doing. So basically what we have here is we've got two computations we want to run asynchronously in the background in the common fork join pool. And then what we're going to do, and you'll see how this all works in a second, we're going to have those computations run, and we're going to use the single.zip method. And single.zip is basically a join method that's used to perform some computation when all the various singles passed to it are done with their computation. So in this case, what we're saying here is when we're done computing the price and when we're done computing the rate, then go ahead and perform the conversion. And the conversion, as we'll see, will apply the rate to the price to get the converted cost. Now, this particular path is going to have a timeout as well. And so what we're saying here is if this whole thing takes more than 3 seconds to run, then we're going to have a timeout exception thrown. So up here, if it took more than 2 seconds to get the rate, we would use the default rate. And then down here, we're saying if the whole thing takes more than 3 seconds to run, we're going to get a timeout exception there. So this is handled in a slightly different way. Finally, from the main program point of view, with this implementation, we're going to do a blocking subscribe, and I just do that so that the test will finish in a sensible way. And it goes ahead and either prints the price, the converted price in pounds, or it prints out whatever the exception was, which in our case is likely to be a timeout exception. Okay, so that's the first example. And I'm going to look through all the details here in a minute. I just want to give you the big picture view at a high level. And that's run concurrent singles. Let's now go down here and take a quick look at run parallel flowables, and then we'll step back and kind of walk through this in more detail. So as you can see here, once again, we're going to do a bunch of iterations. This time, however, we're going to use a flowable instead of using a single. So up here we use singles. Down here we're using flowables. And you'll see in a second why we're using flowables. The reason we're using flowables is because there's an interesting enhancement that was added to RxJava 2 that's called a parallel flowable. And so by starting off with a flowable that is going to basically find the best price from this London to New York, we're going to run this in parallel, and we're going to go ahead and run this in the background, and it's going to go run in a background. It's going to run in a pool that's the common fork join pool. So we'll look at that in a second. If all goes well, we're then going to go ahead and find the best price. And I'll come back and talk a bit more about this later when we compare and contrast this solution with the Completable Futures solution. It's a little bit weird the way we have to do it with parallel streams. I'm sorry, parallel flowables. But you'll see how that works out later. So we basically pass a string up here, and then we take that string and we go and find the best price corresponding to that route leg. And what we get back, of course, will be a parallel flowable that will contain the best price. And then we convert this back into a sequential. And then we're going to go ahead and have another flowable. This is going to do the rate conversion, or the rate computation from pounds to dollars. Once again, we're going to do this in parallel in a common fork join pool. This time we're going to query for the exchange rate, and then we're going to convert this back to sequential. But if for some reason it takes longer than 2 seconds, we're going to use the default rate. So this is much like we did before, just using parallel flowable syntax as opposed to the single or observable syntax. As before, once we get to this point, we've now got, we're now back to things that are going to be sequential. And so these guys will then go off. Once those two parallel computations complete, we're going to zip them together, run the convert operation, give a timeout of 3 seconds, and then do exactly what we did before. We're going to use blocking subscribe to tell us what either what the price was, if we were able to get it to finish in time, or we're going to get the exception thrown. Okay, so that's at a high level. So now let's kind of go back and dig into these implementations a bit more. Let's go take a look at FindBestPrice. So for FindBestPrice, let's go ahead and go to the definition of FindBestPrice. And I kind of left this for the end because it's not really very interesting. What it does is it waits for a random delay, and then it goes ahead and returns some price, right? So obviously production code would not look like that. It would be connected to a web server. So I'm just kind of mocking it for now. Since we're down here, let's go ahead and take a look at query ExchangeRateFor. So it takes a source and a destination. It splits it using a regular expression. We end up with the source part and the destination part. And then we basically go ahead and return the results of this, which again is just fabricated, 1.2 exchange rate. Here's the convert method. This gets used when we're doing the zip call. And you can see that conversions are going to take price times rate. So that's the conversion. Just to keep going, since we're down in this part of the file, here's RandomBleh. RandomBleh is going to generate a delay between half a second up to 4.5 seconds. So you see, sometimes everything is going to work fine if the random delay is less than the timeout period, but sometimes the random delay will be longer than the timeout period. And of course, depending on which timeout we're dealing with, it'll either end up getting a default value for the rate, or it'll actually end up throwing the interrupted exception. So we're going to kind of talk through that when we look at the code and see how it runs. And then we have a little print method that prints out the thread where the operation took place. Okay, so those are basically all the different pieces. Now that we've talked about the code, let's go ahead and run it. You can see what it actually does. And you can see we're doing the singles first, concurrent singles, each iteration. So this iteration threw an exception, so it timed out, so we got an exception. The next one worked fine, and so we ended up with getting the rate comparison and the flight leg working out. And so that worked. Sometimes the exceptions are thrown. And then you can also see here, if you look carefully, sometimes we time out on the rate computation, in which case we get back the one-to-one case. So the three main types of results here are either this one here, where everything ran under the timeout period, and we get the results of taking the price times 1.2, or everything took longer than 3 seconds, in which case we get a timeout exception, or the rate computation timed out, and so we end up getting back the default rate, which is just 1.0. And that shows up down here. And if you look carefully at these things, you can see that we ran it 5 times for the concurrent singles, and we also ran it 5 times for the parallel flowables. And they get, basically the same results, although we're at the mercy of the random number generator to know how long the delays are. But I think you hopefully get an idea for how the program actually runs. Okay, so that's pretty cool. So what we're going to do in a minute is we're going to go over and compare and contrast this with the Completable Futures version. And I'll literally walk through them side by side so you can see in an apples to apples way how they're the same and how they differ. But before I do that, let me see if there's some questions that we might have. So let's go ahead and take a look at the chat window. For zip, we don't have to specify the thread pool in which that'll be performed. That's correct. I think that, of course, will all be something that you can dictate by the compose, excuse me, got allergies. That's all dictated by how we would have that running, and we could dictate where the zip call would run by doing another compose and having it run in the appropriate pool. Zip is very similar to then combine, although as you'll see when we look at the source code, then combine is a little different because it only is limited to 2 elements, whereas I think zip can be used for more than 2. We'll talk about flowables and sequential. Sequential is a way to take a parallel flowable and turn it back into a good old flowable. So flowables by default are non-parallel. That doesn't mean they can't run in, they can't be subscribing or observing on other thread pools. It just means that they're not used for parallel execution using the parallel flowable mechanism. So a flowable is like a single or an observable with one major difference. The major difference for flowables is that they can exert back pressure. And this example doesn't illustrate exerting back pressure, but one of the things you can do with exerting back pressure is you can basically define what happens when the publisher is sending data faster than the subscriber can handle it. And flowables give you ways of dealing with that, and you can actually set various policies to buffer the data, to just take the last item, and so on. This example doesn't illustrate that because we're not generating events faster than we can subscribe and process them. But that's what a flowable does. A flowable allows for back pressure. And if you need to jump back to the user interface thread, there's a couple different things. So keep in mind that in vanilla RxJava, which is what we're showing here, there is no user interface thread per se, although I think there's a scheduler that I think it's the trampoline scheduler or something like that, which tries to run it on the main thread. If you go to Android, there's a variant of RxJava for Android called RxAndroid or something like that. And that actually lets you designate the UI thread as the target for where the operations run. I don't believe that's actually part of RxJava. I think that's an Android-centric thing. And the way to do that would be to do observe on. So there's subscribe on and observe on. And the basic distinction, and we'll go back and look at the code here in a second, but the basic distinction is that subscribe on affects everything in that flow, in that stream. Above subscribe on, down below to the next time some scheduler is invoked, whereas observe on is from where you do the call and downwards. So subscribe on goes sort of up and then down, whereas observe on just goes down. Those seem to be the main distinctions. I don't have an example that shows back pressure, but if you Google, you will find lots of examples. There's some really nice discussions about RxJava by a couple of folks that I have learned quite a bit from, one of which is Tomas Nukowitz, who's got a couple of really good videos, and he wrote a great book on RxJava. It's called Programming RxJava or RxJava Programming or something like that. Maybe it's Reactive Programming with RxJava, I think that's what it's called. And it covers RxJava 1, but it's still a good book. And the other person who always gives great tutorials is Venkat Subramanian. And so I'll try to show you some good tutorials later to illustrate that. Okay, so let us go back now. I want to show you a couple things that were spurred on by the discussion, and then we'll switch over and talk about completable futures. So first, let's go back here. So if you look back over at this code, there were some questions about, oh yeah, let's look at some more of the details because I didn't explain this very well. So compose is an interesting RxJava mechanism that lets you kind of customize the operations that can be in a pipeline or a stream. And what I'm doing here is I'm selecting where I want this thing to run. And the way I'm doing it is I'm defining all these little factory methods that are part of a utility class I call RxUtils, for lack of a better term. And common pool single will take a single and it'll subscribe that single and everything above it and then below it to run in a thread in the common fork join pool. So we say, I want the scheduler to come from the common fork join pool, and I want that computation that I'm describing here, things above it and below it, to run in that context. And you can see that we do something similar for common pool observable. I don't show an observable here, but I can do the same thing for common pool for observables as well as for singles. And then also, if you go back over here and look at the code, and you look down here in the flowables part, you'll see that we have this thing called common pool parallel flowable. And common pool parallel flowable is the same idea, except it's going to take the, actually it's going to take a flowable, not an observable. It was cut and paste there. And it's going to go ahead and schedule, it's going to run the flowable computation in this case, the common fork join pool. And going back to the question from before about how you could designate what other threads you wanted to use, what other pools, you can just put in your favorite pool that's supported from schedulers. And let's just see if we can do this. There we go. So here are some of the various schedulers that you can have. You can have computation, which is meant for compute-bound jobs or CPU-bound jobs. It's a fixed pool. They have something called I/O, which is meant to be a pool that is for I/O, so it can be expanded. You can have a new thread for every computation. You can do it in a single thread. You can do trampoline, which seems to be a little bit murkily defined, but I've used it to get it to run on the main thread with vanilla RxJava. And then you can also say from, and that's what I'm using here. I'm giving it the thread pool that I want it to use, which in this case is a common pool. But in general, you could define a fixed size pool or a cached pool or a non-common fork join pool, whatever pool you want to use, you can get that and connect it to the schedulers from. You can connect it to the RxJava framework with schedulers from. Okay, so that was a couple things. Then the other thing I want to note is whenever we go ahead and use these compose and subscribe on mechanisms, that goes back up, it kind of goes up to the top here, and then all those things are run in that pool, in that scheduler context. And in this case, we're just running it in the common fork join pool. But I think you can see how easy it is to change this. In fact, we could make this whole program be a single-threaded program just by changing it, I think, to use the trampoline, for example. Let's see. Those were some of the things I want to talk about. Let's talk about flowables real quick. So I remember I said a flowable is just it's a stream that can exert back pressure. We don't really do that here. But the other thing is that when you are done with running things in parallel, then you can convert or merge things back to be sequential. And that's what .sequential does. And this is very important to understand because flowables only have a very limited set of things they can do, parallel flowables rather. Flowables can do pretty much everything that observables can do and singles can do, but parallel flowables are restricted in what they can do. And so in particular, you can't put timeouts on them for some strange reason. So I had to convert my parallel flowable back to a sequential flowable. You can see that what happens here, right? We went from flowable string to parallel flowable string to parallel flowable double to flowable double, and then back to the timeout. And I couldn't do the timeout here. I couldn't do this because there's no timeout operation defined on a parallel flowable. So I had to go ahead and basically join it back together in order to put the timeout on there. And that took a little head scratching to do. And we'll see when we talk about completable futures, I think it's a little cleaner. Okay, so, and then of course, if for some reason we wanted to run this, we could always put this on its own thread pool as well. I think it's probably fine where it is because honestly, there's no point in doing the convert operation in a separate thread because it's very fast. But if you were doing a longer running operation than convert and you wanted to make sure that was going to run concurrently, it's easy enough to do that. Okay, so that's what I wanted to cover for the RxJava versions. And of course, I'm always happy to take any more questions you have, but that's a good starting point. So now let's go back and compare and contrast the RxJava implementation with the completable future implementation. I covered the completable future implementation several days ago, but now that you've seen the RxJava version, it may be more interesting to kind of look at them side by side. So let's take a look. You can see that here we have something called default rate. You'll see what that gets used for. This is the RxJava version is down here below in EX5, and the completable futures version is up here in EX27. So notice I don't have to do anything fancy. I don't have to do like a single just or a flowable just one. I just say default rate. So keep that in the back of your mind. A lot of things are more succinct and more clean in my mind with completable futures. We make ourselves a random number generator. That's the same. We have a test program that's pretty much exactly the same. And then let's go ahead and take a look. And I guess we'll compare run concurrent singles with our completable future implementation. If you're familiar with completable futures in RxJava, then you know that a single is more like a completable future than an observable is. And that's because a completable future really is going to return one value, just like a single, whereas an observable can have many values that are part of it. Okay, so once again, we have max iterations. We're going to run this multiple times. And let's take a look. What we're going to do here is we're going to go ahead and make ourselves a completable future to double called best price F for best price future. And that will use the supply async factory method on completable future to go find the best price between London and New York. And notice how the same code down here in RxJava is just a little bit more verbose, because I have the from callable, which is very similar, but then I had to go ahead and compose it with the common fork join pool. And even though I use this compose method and the common pool single, it's still some extra work. And I think the main difference here is that completable futures out of the box were meant to be run concurrently, whereas RxJava out of the box is not meant to be run concurrently. It's meant to be used sequentially, and then you can add concurrency as basically an attribute, which is what we do down here. So I think that's probably the biggest difference, is that RxJava treats concurrency more of as an afterthought, whereas it's a first-class citizen in completable futures. The next thing we do is we define ourselves a completable future called ExchangeRateF, or exchange rate future. And here we go ahead and asynchronously query the exchange rate. And then we go ahead and we connect the timeout, and we say, if after 2 seconds, this operation is not completed, just give it the default rate as the result for this thing. So that's our completable future. And that's actually quite similar to what we have down here. Again, we use from callable with query exchange rate. We have our timeout, looks very similar with the default behavior in case it times out. And then the only difference is, again, we have to add in concurrency as an afterthought. You know, it's an attribute that you add to your stream of flowables, as opposed to being the first-class citizen in the factory method that kicks off the computation that will be running asynchronously as the completable future. Okay, and notice also, by the way, we don't have to designate the common fork join pool. That comes along for the ride with completable futures. Down here, we then have, to Sanjeev's question from before, we use then combine. And you can see that that is pretty much the same as we do here with zip. I think the main difference is I think you could have more than 2 parameters for zip. You can zip a bunch of things together. In this particular case, we're just combining 2 things. And you'll see also, note the similarities here. We have the or timeout, and that looks almost identical. So we say or timeout, and that's almost identical to timeout. And then down here, no matter what happens, when complete will either get called with a value that's meaningful because everything finished correctly, or the exception got thrown. And we can handle those cases very much the same way that we do with blocking subscribe. We either get the normal result or we get the error result. We can differentially handle them. When complete is a very interesting call, by the way. You can do a lot of cool things with it. And hopefully in the not too distant future, I'll show you some other cool examples using when complete. When complete is interesting because it always gets called, and you can do an arbitrary thing with a side effect inside of when complete. So that's kind of an interesting feature that I'll try to show you in another context later. We then go ahead and swallow the exception in case an exception is thrown. We don't want it to blow the program up. And then we block until all the asynchronous processing completes. And we can do the same sort of thing here. The blocking subscribe kind of combines the features of when complete and join, and I guess to some extent exceptionally. So you can see that it's a little bit more crisp here than it is with completable futures. Otherwise, everything else is the same. All the little helper methods are identical. So just for kicks, let's just zip back over here real fast, and let's open up the completable future project, and let's go ahead and run it. And I think you'll see it should behave essentially the same way that the RxJava one did. You can see, depending on what happens, depending on how the random timeout works, sometimes we get an exception. Sometimes we get an exception for the exchange rate, in which case we get the default. Other times we actually compute the exchange rate, and so on and so forth. So, and you can also see if you run both programs, you can see that the computations take place in different threads. And you can control that to large measure with both of the frameworks. Again, I think the main difference in my mind is that the Completable Futures version is just a bit more concise because it bakes in concurrency as its very essence, whereas with RxJava, it's something you add on to it through compose or subscribe on or run on or whatever. Also, just to reiterate a point I made the other day, for my money, RxJava programming looks a lot more like parallel streams than Completable Futures. But from a performance point of view, it performs more like Completable Futures than it does parallel streams. So Completable Futures are typically more efficient and faster and more scalable than parallel streams are in Java. And RxJava does a nice job of giving you the convenient programming abstractions that you come to expect from parallel streams, which are, in my mind, more intuitive than Completable Futures, while preserving a lot of the performance of Completable Futures. So it kind of gives you a best of both worlds type of approach. Okay, so that's what I had wanted to cover today. Let's see, there's a bunch more questions, which is fantastic. Let's go ahead and take some more questions. Bring back the chat window here. Let's see. So subscribe on. What happens with subscribe on? I think I showed that. This is back to the RxJava version. For subscribe on, what you basically see is that when you subscribe on something, then wherever the source of the event comes from that point onwards and downwards, it basically subscribe goes up to the source and then down. And of course, you can have multiple subscribe on calls per flow, per stream, just like you can have multiple observe on calls per flow or per stream. In fact, just for kicks, let me go over here real quick and reshare my screen. Let's go over here and let's say subscribe on versus observe on RxJava. And if you do this, you'll find some really interesting discussions here talking about these different methods. And they'll pretty much say what I just told you. But you can also walk through them and they'll explain them and they'll tell you what the different kinds of schedulers are. This is an Rx Android oriented website. So you can see that they have this Android schedulers.main thread, which gives you the UI thread. That's not part of RxJava. But basically you can kind of see the discussions. And here's where it talks about subscribe on versus observe on. So subscribe on affects upstream operators above the subscribe on, and then down below, and observe on, in contrast, affects downstream operators below the observe on. And then they show a bunch of examples that illustrate you can mix and match these things. One of the somewhat quirky aspects of this that you need to be careful about is it's very easy to move computations between different threads with RxJava. And it's syntactically almost trivial to do that, but you have to be careful because moving things between threads has a cost. And I think we all know it's context switching and synchronization and data movement and all kinds of other stuff, cache invalidation. So just because it's trivial to do it doesn't always mean it's a good idea to do it. And let's see, another question. If the program is run on a CPU with a single core, will it work? Yes, of course. All this stuff is completely orthogonal. It's going to use the underlying thread package, which these days in modern Java will always be preemptive threads. What's the difference between asynchronous and reactive? Well, that's a good question. So there's different points of view on this. So asynchronous, in my mind, is always with respect to something. So something is asynchronous if it's running, in the background or running concurrently with something else that's going on in the foreground. So you might, for example, great example of this would be Android, where you want to do synchronous operations in the UI thread. In other words, operations that don't block for very long. And anything that has to take place that's going to block, you run asynchronously in some background thread using something like, say, the async task framework or whatnot, or RxJava or parallel streams. And the idea there is that the UI thread, the main thread of control, does synchronous operations. And when it has something it wants to take that'll run for a long time and may block, you run it asynchronously. But it's running asynchronously with respect to the user interface thread. Reactive is a similar concept, but you notice that it doesn't necessarily have to be asynchronous. You can have synchronous reactive programming. In fact, that's what you get out of the box with RxJava. So RxJava out of the box is synchronous reactive programming because there's only going to be one thread of control. And so it's only if you start doing tricks or using operations that will move things between different threads that the asynchrony part actually makes a difference or actually matters. Let's see. So, go back to Completable Futures. My point about Completable Futures versus RxJava. Completable Futures, you really can't start a Completable Future without having it run concurrently, right? So the two ways to kick things off with Completable Futures are either to use supply async, which is what I showed here, or run async. Both of those end up running the computation in a thread in the common fork join pool by default. And so just by its very nature, it's doing things concurrently. In contrast, RxJava by default is not doing things concurrently. It's doing things reactively, but it's not doing things concurrently by default. And it requires you to use these subscribe on or run on methods or other things like interval, which will work in the background and do its work asynchronously. So RxJava by its very nature is not asynchronous. It's if you tell it to be asynchronous by using subscribe on or observe on or run on or whatever. So that was my point. And you can see literally when you look at the code, if you look at the RxJava code versus the parallel or versus the Completable Futures code, you can literally see that when you start something with Completable Futures, it's running asynchronously. There's no need to do anything else. There's nothing else you can do. You have to start it running asynchronously. Whereas with RxJava, you've got to be explicit. If we don't put this compose method here and subscribe on or run on, it's going to run in one thread, and it's perfectly happy to run in one thread. And then that's not a defect. That's just the fact that they don't make it concurrent by default. Whereas with Completable Futures, it's concurrent by default. WhenComplete probably runs in the same thread which the Completable Future runs, but blocking complete probably runs in the caller thread. Yes, that's most likely to be the case. And the easiest way to figure that out is just to run the program and look at where the print statements are coming from, and they'll tell you where they're running. Yeah, so let me reiterate the point about subscribe on. You can put wherever you want to put subscribe on, it'll start with whatever is the earlier thing, which could be a previous subscribe on, and it basically whichever one comes last, I think, wins. But it starts at the source and then continues going down below. Let's see. Any plans to continue the webinar? So as I come up with new things to talk about, I'll continue to do this. I have a vast amount of stuff, as you no doubt notice if you go to my website. And so I'll just have to kind of pick and choose to see what's most interesting to the user audience of these things. There's lots more RxJava stuff that I could cover. Some of it's not particularly very interesting. It's just demonstrating little things of RxJava or little things of Java 8. So I'll kind of pick and choose. But I have enough stuff for the time being to keep going. Okay. So let's see. If there's any more questions, I'll be happy to take them. Otherwise, I think I will go ahead and sign off. Oh, before I do that, though, let me just show you one more thing. Let's see. I always can never. There we go. Here we go. This is the guy I was telling that Thomas Nukowitz. I'm sure I'm completely butchering his name. but I'm sure I'm not the only one. He has got some really interesting tutorials. He's got this interesting tutorial on RxJava and legacy products, or legacy projects, which is quite worthwhile to watch. He also wrote this book about RxJava. He also has written really great papers and given really great tutorials on Completable Futures. So anything asynchronous, he's a great resource. And then he has another guy who they apparently went to the same school together. Let me see if I can find this. Streams and Completable Futures. So if you go over here, there's I'm not even going to try to pronounce this name. I apologize profusely. It looks like Gregor's, maybe Gregor's. So let's say Gregor's. And again, I apologize if I don't get the name right. He's got some really cool stuff talking about completable futures and combining them with streams. And so I was poking around the other day and found this very interesting article. And this article is cool, but what's really cool is if you go to his Parallel Collector website. Let's see if I can find that. We go, Parallel Collectors. If you go to the Parallel Collectors website, he's got this really cool little framework for parallel collectors. And what's interesting about this is that it's clear he and Tuomas know each other, and they've sort of thought similar things, because if you read some of the stuff he's got in here, like his future collectors, it's very much like some cool articles that Tuomas had written about back in the day. So really cool stuff. He also taught me something very interesting. Let me see if I can show you this. So Java 9 count operation. Let's see if we can find the link I was looking at the other day. This is absolutely insane. So let's go take a look at Java 9, and we'll go find stream, and let's go find count. This is one of those things where you just have to be like, what were these guys thinking? Here we go. So this is so bizarre. I've got to find a way to work this into one of my tutorials. It used to be the case if you had a Java stream with count as the terminal operation. So count basically just counts the number of elements in the stream. In Java 8, it would do all the operations, the intermediate operations in the stream, and then return a count of the number of items. That makes plenty of sense. Well, for some really weird reason, in Java 9 and beyond, they changed it. So if you use count, the system is free to get rid of all the intermediate operations that you had that don't affect the size of the stream. So like filter would affect the size, flat map could affect the size, but peek or map don't affect the size. And they can just optimize those calls away altogether and just return a count, which just makes no sense whatsoever. So, and if you read this description, in fact, that's what it says. And if you read on the web, you'll find a couple of places that talk about this. I think it's the strangest optimization I've ever seen in my entire life, because it just breaks everything for no good reason. It's like, what was the point of that? So anyway, Gregor's kind of clued me into that the other day, and I was very surprised to learn about that. And so I totally see for peek that this optimization makes sense. The problem is if you use it for map, then it no longer makes sense. And apparently, it is not clear to me. If you take a look here, if you read this thing, really like a language lawyer, it says, let's see, an implementation may choose not to execute the stream pipeline if it's capable of computing the count directly from the stream source. Okay. In such cases, no source elements will be traversed, and no intermediate operations will be evaluated. Behavioral parameters with side effects may be affected. So, yes, of course, peek is meant as a debugging tool, but map is not expected to be a debugging tool. Map is expected to actually do something, or could be doing something. And so the semantic, the interpretation that Gregor's shared with me was that map could also be omitted as well. Now, I have not personally seen that behavior, but it makes it sound as if that could be the case. So It's completely ridiculous. I just have no idea why they would break code. And I've actually used this stuff before. Yeah, it's just weird. There are actually good examples of where you would want it to behave in this way, where you'd want map to be called, because it does have side effects. But I agree with you that, I guess, strictly speaking, from from a functional programming purist point of view, you might think, oh, well, map shouldn't have side effects. The problem is that Java is full of side effects, so it seems inconsistent. Let's see, another question here. How do these technologies differ from Kafka streams and Spark streams? I've never used Kafka streams or Spark streams. I've got to believe that they're always pretty much the same. One of the things I've learned as I've been playing around with RxJava and streams and so on is that they're all very similar. You know, the concept of fluent interfaces used to connect operations together in a pipeline, very, very canonical. It's a common pattern. So if someone else wants to take the time to learn the differences, I'm sure that there's many places that will explain that, but I haven't got a chance to do that yet. Okay. Well, again, everybody, thank you so much for joining. And I will go ahead and render this video here shortly. And I'll send out announcements with next week's schedule as soon as I have a chance to think about what we'll cover. So thanks again, and I'll hopefully talk to you again soon.